Hi, everyone. To those of you still signing on, welcome to what I hope will be the first of many HyperX webinars. Big thank you to all of you for taking the time to join us today. I'm Charlie Cahill. I'm the Director of Customer Operations here at Collier Aerospace, and I'm the host of sorts for this session. Before we jump into it, a few housekeeping items. You'll notice on the right-hand side of your screen, we have a few different places where you can interact both with us and with each other throughout this session. So at the very top, you have the chat function where you can post miscellaneous comments and chat with each other as attendees. We also have a specific Q&A section right below that. You can use this to type your questions as you think of them. I plan on monitoring that throughout August's presentation. So any question that I can answer quickly, I will do so there. Otherwise, I will elevate it to August during the live Q&A at the end of the session. And then in a few minutes, we will also be presenting you guys with a poll question. So we'd be curious to get your feedback using the poll section there as well. So one last thing on my list before passing the ball over to August, I'd like to share my screen really quickly. View the world or view the digital thread. So up here at the very top, we have the HyperX database. As you probably know, the HyperX database contains your margins of safety as well as your sized model or your size design. It sits squarely in the middle of the left-hand side, which is the FEA or the analysis side of the house, and the right-hand side, which is the CAD or the design side of the house. Those of you that have been longtime customers might be aware. Historically, we couple very, very closely in this workflow here, the left-hand side of the house. We are considered a stress analyst tool. HyperX will easily import your finite element model to understand the geometry, your elements and properties, and all of the loads that are on your model. And it will automate the sizing process of that finite element model and spit out those updated FEM properties into an updated run deck that you could then run through FEA or perhaps pull back into your pre or post, whatever you might want to do with that. Like I said, we've been doing this pretty well for on the order of 25, 30 years now. But in recent years, it's come to our attention that as the originator of the sized design, it's important for us to also just as easily couple with this CAD side of the house, the design world. There's maybe two different ways to think about that. Coupling with the design will help the analysts better couple their design or tailor their design towards features that are in the CAD. And it also helps to more readily get the sized HyperX results into the CAD file itself. The other thing I'll note here is our goal is not to present to you some amazing push button, we have solved all of your digital thread problems type solution. I think we all know and can realistically understand that the digital thread and coupling FEM to CAD is a much larger problem than more than one software product can solve. But the features that August will share with you are ways to sort of bridge that gap, bring your analysts and your designers a little closer together in a more convenient and efficient way. So with that being said, I will pass the ball to my colleague, August Nover, the Director of Research. He's also the lead engineer on this CAD effort with our developers.
All right, thanks for that introduction, Charlie. Yeah, as Charlie mentioned, I'm the Director of Research, and I'm excited to share these new features that we've been working on to interface HyperX better with various CAD software. So yeah, without further ado, I'll kind of jump into the technical details of these features. Get my screen share going here. The PowerPoint slides just to kind of introduce the story and motivation, and then move on to a live demonstration of those features. So just kind of reiterate the objective of this webinar. We're trying to provide an overview of new HyperX features that enable users to consume CAD models, to review them and update their analysis, as well as provide optimized panel geometry back to CAD designers. And in these two workflows, we're making emphasis on continuity of data between HyperX, CAD, and PLM, all in the name of more efficient iteration of your structural vehicle design. So as I said, I'll start off, take about 45 minutes here, start off with a few PowerPoint slides, and then jump into a live demo of CAD import, and then another live demo of generation of optimized stiffener geometry. A little further motivation. I think this topic is probably pretty well understood by everyone, but I'll sort of set the groundwork here for the motivation. So why is the digital thread important? Obviously, we know a lot of people are still kind of struggling with what we might call, a legacy approach where we're exchanging design data between disciplines, namely FEA and CAD, in disposable or untracked files. We have people who are creating screenshots and PowerPoints of design details and using that to emailing things back and forth to people, and it's not a good way of, or there's no consistent way of tracking that data or versioning that data, and it's easy to sort of lose track of the current state of the design. So we're helping. Our objective is help our users move from that world into more of a digital thread type of world where they can kind of more seamlessly pass data back and forth with other disciplines via CAD formats that other disciplines are used to working with, step files, IGES files, and all sorts of other formats. So with HyperX, we're, as Charlie mentioned, trying to find kind of the middle ground between full automation of this data exchange and more of a somewhat man-in-the-loop approach, but still automating the handoff as much as possible. Mostly just limiting it to an import and export on either end, rather than having to interpret design data out of a PowerPoint, for example. So this flow chart shows the general process involving HyperX and CAD. On the left-hand side, we have our CAD import. So we've recently added support for a number of import formats for CAD. The idea being that you would pull in sort of the current state of the CAD design into HyperX and interrogate that CAD model and use it to better inform your analysis and optimization setup in HyperX. And then on the right-hand side, we've got a number of new CAD export features. Everything in green text is something that we've added in our latest release as of the July timeframe this year. So there's a variety of things we can now include in a CAD export. We can generate stiffener geometry of our optimized panel designs. In the CAD file, we can include metadata, annotations, so dimensions and other fastener callouts and things like that. We can also pass out optimized dimensions in the CAD file, as well as composite ply data, which is related to the workflows I'll be showing, and there's a lot more that can be shown here. Likely save that for a webinar for another day. And then down at the bottom left is a table that summarizes all the CAD formats that we now support for both import and export. Again, the green text highlights recently added features or recently added formats. We'll pause briefly here. I think Charlie's going to run a poll. Kind of just curious to see, which CAD platforms our users are working with, so we can kind of better understand, which areas to support.
Yeah, so on the right-hand side of your screen, I just opened the poll. See some responses coming in. A few for NX, a few for CATIA. More coming in as I'm saying these things.
Live competition here.
Yeah, it is. It's almost like a race.
All right, we've got CATIA and NX are neck and neck, and then a few in the other categories. I'm kind of curious to know what the other categories are. They're the 11%. Maybe if at the end, if whoever's in that category maybe want to drop the name of the CAD software you're using into the chat or something, feel free to do that anonymously. All right, so yeah, we've got plenty of support already, I think, in the areas that people are responding in, but any that can be added, we'll definitely look into that. Okay, so kind of changing gears here, move into the live demonstration portion. First showing the CAD import into HyperX, and there's a table down at the bottom just reminding you of the formats we support there. So the just to sort of set the story here for the live demo of the import. Our mindset for this part of the demo is we're a HyperX user who has imported a FEM, and they're ready to perform analysis and sizing. Some objectives here: we want to import our CAD models and overlay them on the FEM, locate design details such as cutouts and fillets that are not in the FEM, and then sort of slice up that geometry and extract dimensions to be used in our analysis. All in the name of enabling stress analysis in HyperX to collect geometry data without having to rely on an external person, a CAD designer, or having to open another software to do that. And with that, I'll switch over to the HyperX viewport. So for both parts of the live demo, I'll be using this UAM model. It's a urban air mobility wing. We've got the kind of the main wing box structure included, as well as some elements of the leading edge and trailing edge. So to kind of start things off here, I will import a CAD model of the of kind of the current state of the design of the structure. I'll import a CAT part, a CATIA part file. Importing a single file here just for the sake of keeping it simple, but you could import multiple files at a time. Say if you had used a assembly type of organization with one CAT part per physical part, you can import it that way as well. And the model's loading. While it's doing that, I'll point out we have a CAD tree to help with the organization of the model, and it'll populate in a second here once the model's loaded. This is meant to be kind of in parallel to the typical structures tree where you manage the HyperX structures. All right, so our CAD model is loaded. Initially, we see it sort of displayed on top of the FEM. You can see the FEM and the CAD kind of peeking through each other. We'll focus on the CAD first. So I'll just hide the HyperX structures. And yeah, one of the first things we'll look at here is well, I'll just hide the upper skin, and I'll also expand folder here, so that the entire CAD model went into this one folder in the CAD tree. Zooming in a little bit, you can see this CAD model has some bit of detail to it. So everything is modeled as a solid body. We've got thicknesses on our ribs and spars, and some joggles in the ribs going over the spar caps and whatnot, as well as some fasteners discretely modeled. So one of the first things you can do with this imported CAD is maybe just sort of compare the state of the CAD to your current FEM, and sort of uncover things that might be missing in your FEM or your analysis setup that you need to be accounting for. So for example, the ribs, they don't go all the way to the end of the trailing edge, so maybe you need to consider adjusting your FEM. Or here in the middle of the rib, we have these cutouts, which are obviously not modeled in our FEM either. We could either request a FEM update, or maybe we have some sort of cutout analysis plugin in HyperX, which I'm not going to show here, but that's a possibility with our analysis plugins. So for that, let's say, for example, we want to go in and quickly measure the diameter of those cutouts as an import to our analysis plugin. So I just popped open our measuring tool, and I can just easily grab the diameter of that cutout, which is 3.5 inches. Another area where the measuring tool can be quite handy is for measuring things related to fasteners. So in this example, again, we've got some discretely modeled fasteners here. They already have some points dropped on the center line of the fasteners, but you can also do that with utilities within HyperX. So let's kind of imagine that we've got a edge joint set up here in our FEM, where we want to do some analysis and sizing of those fasteners. So to do that, we would need a fasten joint analysis property, design property, which I just opened up here. And there are a few kind of key inputs that we would need to grab data from the CAD to populate the settings. The first being spacing. So we could, again, open up our measuring form and measure the distance between these two center lines. So our spacing here is 1.571 inches. And then for the fastener selection itself, let's just do a show only on the fastener and zoom in a little bit. So maybe just by visual inspection, we could identify that's a Hylock 10 fastener, or sometimes people like to sort of imprint the name of the fastener on the head. Many different ways to do it. So we know it's a Hylock 10, but we need the diameter of the fastener in that location. So we'll again use the measuring tool to just grab that real quick. Measuring from one side to the other. So it's a 3/16 fastener. I'll open up our fastener selection dialog on the design property. And here are Hylock 10s at the top. Dash 6 is our 3/16, and we could actually just pop open the fastener editing form, quickly compare the the drawing for the fastener to the CAD. Looks like a good match, and we would assign that fastener to our joint design property, and be one step closer to being able to analyze and size with that fasten joint. All right, let me just re-show the rest of the CAD here. Hide the upper skin again. So another thing that measuring form that I've been showing is quite useful for is collecting large numbers of measurements. It's kind of, the form itself has been optimized to work well in that manner. The form here is actually it's a table type of UI control, so you can easily copy from the form to Excel if you need to collect a lot of data and work with it externally. So what we'll do is, I meant to show this earlier, but here in the CAD tree, it's easy to organize stuff into folders or subfolders. So I'm going to create a folder that's my fastener points, and then I'll open the measuring form back up, and I'll just select that entire folder. So you can see it's populated my measuring form with every single point in that folder, and it's put all those points in the from column of the measurement, and then I'm just going to go in and select a single point in the to column, and now it's measuring the distance from that leftmost fastener to all the other points in that selection. So again, you could easily just copy this entire table and paste it into Excel and do some Excel magic to pull out the spacing in each of these bays, and then again pull that data into your appropriate design property and proceed along with your fasten joint analysis. One other thing to show here, you can also check the components in the XYZ direction for each of those measurements. And additionally, if you have a certain coordinate system you want to be doing that measurement with respect to, you could select a coordinate system there as well. And that coordinate system could come from either FEM or you can create one here in HyperX. I should also briefly mention that all these operations I'm doing with the measuring form with CAD entities are also applicable with FEM entities, such as nodes and elements or zones in your FEM. All right, so I'm going to clear those fastener measurements. There's kind of one more CAD import related story that I'll show here before moving on to the export, and that's related to the spars. So let's kind of pretend here that maybe our spar geometry is fairly locked down. Let's say our team is moving on with procuring the tooling for the spar, so we can no longer change the width of the foot of the spar, but maybe we're still allowed to change the the thicknesses of the spar. So our FEM has the spar cap modeled as a bar element here, and so that there's no width of the spar cap sort of predefined in the FEM. What we'd like to do is get the width of the spar cap from the CAD, assign it to the design property for the FEM spar cap, and then do some sizing of the thickness of that cap in HyperX. So to do that, we'll want to slice the spar geometry at a certain location, and I'll do that with a plane here. I'm going to create a plane that is perpendicular to the spar cap. So I'm just going to grab a curve on the edge of the spar cap. I'll define the position of the plane as a percentage along the curve. And there's my plane. So the next thing I'll do is perform a split operation on that spar. So we have a CAD utilities button here on the menu with a few different options. I'll be showing the split, but you could also perform a intersect here, which would essentially generate a 2D profile of the spar, profile at the location of that plane. But yeah, we'll show the split here instead. So I'm going to select my spar solid body and the plane, do a quick preview. This is just so I can decide kind of which side of the split I want to keep and discard. You can also keep both sides if you'd like. The green shows the side that we'll be keeping. Let's try that again. I think I misclicked there on something. Okay, so we've got our split spar. Again, we'll just quickly grab the width of that cap. And then from edge to edge. So that's a 2-inch wide cap. And we'll now go into our design property for that spar cap. I'll just right click on it and bring up the design property. So the design property is partially set up for us already here. The thickness of the spar cap can vary from 8 plies to 80 plies, but there's no inputs yet for the width of the flange. So we'll go ahead and type in that 2 inches and click apply. And we're now kind of fully set up and ready to size those spar caps. So I'm just going to size all the caps here on both spars. And I'll hide the CAD for a moment, and we'll just look at the spars. I'll turn on the spar cap thickness view here, and we'll plot some data with the legend. So first thing we see, positive margins of safety, which is always a good thing to check first. Look at some of our sizing results. We see for the width of the spar flange set to 2 inches all the way across, which is what we gathered from the CAD. And then going to the thickness of the spar cap, we can just look at our total ply count, and we see it varying from the neighborhood of 60 or 70 plies here at the root of the spars down to close to our min gauge, about 10 plies down at the tip. So we were able to perform sizing in HyperX using some setup information that we gathered from our CAD model. And with that, I'll move back over to PowerPoint briefly here to kind of set the stage for the next part of the demo. So we'll talk more about the CAD export side of the story now. In particular, we'll be focusing on the generation and export of stiffened panel geometry. So these hat stiffeners will be what I'll be demonstrating. Again, kind of setting the stage here with the mindset. We're a HyperX user who has performed some detailed sizing, and they're ready to iterate their design with a CAD designer. Some objectives of this part of the demo will be generating CAD for optimized stiffener geometry, both uniaxial and grid stiffened. We'll export the CAD designs in standard CAD formats, while I'll be showing the JT format in particular. And we'll also include some metadata in that CAD format. And the objective here is to be able to hand off optimized geometry and metadata to CAD designers in CAD-friendly formats. So with that set up, I'll hop back over to HyperX. And for this part of the demo, I'll be focusing on the upper skin of our wing structure, and in particular, looking at the zones in the sort of like the wing box portion of the wing, where it's bounded by the spars, the forward and aft spars on either side. And for this wing, I've got some design properties already set up for sizing. So I'll just open those up briefly and describe the setup. As I mentioned before, this is a fairly mature sizing setup where we've already got our geometric variables, our height and our spacing and the width of the foot and the crown are already essentially locked down from maybe we did some trade studies at HyperX, or perhaps use the new HyperExpert tool to do trade studies. and sort of identified the best, manufacturable geometric variables for this wing cover. I can open up the design overrides form here, and you can see that we have those geometric variables defined basically for every single zone in this part of the wing cover. So the spacing, for example, is largest here at the root of the wing, and then as the wing tapers, the spacing tapers down to a lower value out at the tip of the wing. And same story could be told for the height and width of the stiffener. And then for the laminates of the stiffener, we have some laminate families already predefined. Laminate families are kind of our go-to composite sizing approach in HyperX for sort of a more mature sizing design stage. So for the skin, we have this laminate family where it's able to choose between any of these 6 laminates during sizing. And then for the stiffener, there are 111 laminate candidates that it can choose from. I can show the cross section of one of them here as an example. So for this portion of the stiffener, it's choosing between one of these candidates. So we're set up to size this portion of the structure. I'll go ahead and click the sizing button. And sizing is complete. So we'll now look at the sizing results or design result for one of these zones. So of all those laminate families or laminates in the laminate families that I showed previously, it again selected one for the skin and one for the stiffener. And then also we've got our geometric variables here shown on the design result form. We can also look at the size cross section here in this 2D viewer, which shows the geometry, the size geometry to scale, and also shows a visual of the selected laminates for skin and stiffener. So it's worth noting that the current setup here in HyperX is with what we refer to as a smeared stiffened panels. So the impact of the stiffeners is entirely captured within the stiffness formulation of those shell elements. As you can see, there are no discretely modeled stiffeners on this skin. So what that means is if we want to hand this design data off to a CAD designer, they of course think in a 3-dimensional world, we've got to convert this 2-dimensional smeared geometry into a 3-dimensional body, basically, to be able to perform the handoff. So I'll now move on to the utility that we have in HyperX to do that. Kind of the first prerequisite for generating that 3D geometry is the creation of something we call guide curves for the stiffeners. Again, there's no information in this model to tell or to describe the exact placement of a given stiffener. So what we're doing here is based on our sizing results and our design property setup, we're going to create some curves that have a spacing that represents what's being analyzed in the structure. So first step to that guide curve creation is I'm just going to drop a center line down on the wing skin here, just a couple of CAD points, followed by a CAD curve between those 2 points, or a line, since there are only 2 points here. And then we have this parallel curve generation utility, which is one way to generate these stiffener guide curves. So I'll select the center curve here, the zones. And the reason for selecting the zones here is just to tell us, or to tell the utility basically what surface to follow when it's generating those parallel offset curves. So for the offset spacing, we're going to use 4 inches. and we'll generate 3 curves, forwards and backwards. And I'll just click the preview button here. And we'll take a look at the curves that it's going to generate. So as you probably guessed, the curves that we get here aren't perfectly suited for our structure, because we have, as I mentioned earlier, we have some taper to this wing box. It's wider at the root than at the tip. So what that means is if we generate some parallel guide curves, they sort of start to go outside of the wing box area. They start to cross over the spar locations, which for some types of structures, like maybe a commercial aircraft type of wing, you would just sort of terminate the stiffeners somewhere further back, and maintain its parallel spacing. But for other types of structures, such as the one we're looking at here, you would probably want to taper your stiffener spacing so that you can keep all of your stiffeners continuous. So we do have a number of tools in HyperX that allow you to generate tapered guide curves. Just to keep things brief here, I'm not going to show all the steps, but I'll describe them. Here. So I've got the curves, tapered guide curves, already pre-generated. Basically, the way I created those was to first generate a curve at the root edge of my zone down there, and then at the tip edge of the right-hand zone. And then we have a utility that will create multiple evenly spaced points along each of those curves, which you can see here. And then it's just a matter of connecting the points with curves to create your stiffener guide curves. So now that we have those guide curves, we can proceed with our stiffener generation. So I'll open the stiffener generation utility. It's worth mentioning that I'm showing this for smeared panels, but you can also do the same stiffener generation for discretely meshed panels where you have bar elements that represent your stiffeners, as well as for beams. For example, we could do this with the spar cap bar elements that I was showing earlier in the import demo. But I'll select the smear option, since that's what our design property is using. And for our zones, we'll select those wing box cover zones. And then for the guide curves, I'll just click on that folder that has all of my tapered guide curves in it. There's a few other settings on the form, which I'll talk about in a second. But for now, we'll just proceed with the stiffener generation. So we can see that some new things appeared in our CAD tree. There's basically one CAD folder per zone to organize these generated solid bodies. So flipping the skin over here, we can see on each zone for each stiffener or each guide curve, we have this stiffener representation. Again, it's matching the sizing results that were generated previously. And we can see that our stiffener height, as we go down the wing, the height tapers, the spacing tapers, and the width of the stiffener also tapers according to our design property setup. And the thickness tapers as well, although it's a little harder to see since they're fairly thin. So yeah, we've now generated some stiffener geometry, and we're ready to maybe start iterating this with a CAD designer. Before we do that, we'll first take a look back to the CAD geometry that we imported previously. So having that geometry in HyperX alongside our FEM, really kind of enables us to think a bit like a CAD designer before we actually even go through the motions of handing this data off to another person. So we can take a look and compare, where our stiffeners are landing relative to other parts of the structure, and maybe identify some issues before we hand the design off. So one that might be jumping out at you already is we've got this kind of clash between our foot of our stiffener and the spar cap. They're basically, edges are nearly touching, which could be a problem from a assembly point of view. So what we might want to do is perhaps change the spacing of the stiffeners. Maybe have fewer stiffeners, but those stiffeners could be a little bit larger, and then resize and regenerate some new stiffener CAD. So we can do that now. I'll just hide the CAD again, and we'll just delete these stiffeners. So I already have some new guide curves predefined here. We went from 7 stiffeners to 4 stiffeners, and I have a HyperX design property already set up to mirror that 4 stiffener configuration. I'll just open it up briefly here, and we'll look at the dimension overrides form. We can see here our spacing, our tapered spacing has been increased. We were more in the like 3 to 4 inch range previously. Now we're in the 4 to 5 inch range on our spacing. So what HyperX will do is with these new geometric constraints applied on our design property, it's going to just resize the stiffeners to match that new geometry. So it'll probably select different laminates from our laminate family, still give us positive margins of safety, but just a bit of a different design from the sizing. So I'll go ahead and rerun the sizing. Just briefly open the 2D viewer. So larger stiffener than before, and we'll now run the export utility again, or sorry, the CAD generation utility. For smeared panels, select our zones again. Select our guide curves again. There are a few other settings here that I mentioned. You could choose to generate a mid-surface geometry if you wanted to do some meshing with this. There are also some settings that dictate the stiffener position with respect to the shell elements, which side they're on, and whether or not they're offset from the shell elements. You can also choose to generate a bounding surface as opposed to a solid geometry. And then there's an option to generate 2D profiles alongside the solid bodies if you prefer that format. But I'm going to stick with mostly the same settings I had previously, and we'll generate our new stiffeners here. So we've got our improved stiffener geometry. We'll just briefly check for conflicts. We can see we've got a nice spacing now between our stiffener foot and our spar cap. So now we're ready to actually export this geometry out to CAD. Before I do that, well, actually, there's one other thing I wanted to show with regards to geometry generation. Just wanted to show the same thing can be done with orthogrid panels. So let's say we had the rib set up with an orthogrid. We could easily run the same little utility and get our orthogrid geometry and include that in our export. Just a little side note there. I'm not actually going to include that in the export. Okay, so going back to the wing cover, one last step before we do the export, and that's to add some metadata to the export. And we'll do that through our legend probe in HyperX. So the first thing I want to add to my metadata here is a PLM part number. And these were previously imported into this model as discrete fields. So it's basically just a custom data field that I imported from an external source mapped to a zone ID in HyperX. So I'll add that to my label here. That way, when the CAD designer imports this data, they'll see a part number that they're familiar with, and they kind of immediately know where that information should be going in the CAD model. Along with that part number, we can include stuff like sizing results, just to add a few examples here. So stiffener height, we'll add that to the metadata, and then maybe our thickness and our width of the cap of the stiffener. Along with that, if you're feeling generous, maybe you would include something like the margin of safety of the zones. So we could add that to the metadata as well. That way the CAD designer might have a better feel for which parts of the geometry they might be able to change more freely than others. If you have a low margin of safety, probably not much wiggle room in the design, but if you have a higher margin of safety, maybe there's more room for change in that area. So we'll include this this geometry, this metadata in our export. Let me just sort of reorient the model here for visibility. And we'll go to our CAD export. And for this export, I'm going to use the JT format, which natively supports this metadata that I've added to the file here, but you could really use any, if you wanted just the geometry, you could use pretty much any format you'd like. And I should mention this step format also supports the metadata that I've added. So I'm exporting that file, and now we'll hop over to NXCAD and just briefly look at what that generated CAD file looks like on the receiving end. So here in NX, I'm just going to drag and drop my exported CAD file. And fit it to the view here. So we can see all of our exported solid bodies. First thing that pops into view. And then I just need to do a brief convert command here on the imported annotations so that we can view those. And here we see those pop into view as well. So we've got our PLM part number. So that would make us happy as a CAD designer. We know what this solid body belongs to, and then we see the other generated data that we added to the annotations. So we completed the handoff, and from here it's kind of up to the CAD designer to use this information to update their model accordingly. Obviously, we're not expecting this geometry to be the final part CAD for the stiffeners, since there are discrete steps in the stiffener thickness and height and all that. We're expecting this to be more or less reference geometry, help the designer understand what the HyperX user wants, but there's obviously some cleanup needed to create the final part. And then last thing I want to show here is I'll just copy the geometry over into the full vehicle CAD. So another thing you can do here as a CAD designer is understand what impacts those stiffeners might have on other parts of the geometry. Maybe start understanding where mouse holes need to go for the stiffeners, whether or not they might conflict with other parts of the ribs, and that sort of thing. So I'll just transition back over to PowerPoint here and kind of wrap things up. I'll very briefly touch on another topic. This is, kind of a topic for another day. I just wanted to sort of tease it. We'll likely have another webinar covering this, but there's a very similar kind of parallel story to be told with composites specifically. So we can import ply boundaries and export ply boundaries in a very similar manner to what I've shown today with stiffeners. And then moving on to the wrap-up slide here. So key takeaways, I showed the CAD data imported into HyperX, the goal being to import and overlay that geometry on the FEM to locate design details that we don't see in our FEM, and then extract geometry and other information to be used in analysis, all with the goal of enabling stress analysis to collect that geometry data without relying on external CAD designers or software. And then for the CAD export story, I showed generation of optimized stiffener geometry exported in a standard CAD format, along with some metadata to inform the CAD designer of the optimized part geometry all handed off seamlessly in a CAD friendly format. And with that, move on to Q&A. We've got about 6 minutes for Q&A.
Thanks, August. Well done. There was a question that popped up earlier on in your presentation. So you showed exporting HyperX metadata to CAD, but there was a question on, does the part number get imported with the CAD of the fastener or any other data? So I guess, does HyperX take in metadata from CAD would be the...
Yeah, not yet. That's kind of the next step for our CAD import is to, it's referred to as PMI specifically, import that PMI from the JT file or step file, for example, and add it to our viewport. The metadata that I showed kind of at the end of the demo was just imported in kind of a tabular format, and there was a link between the PLM part number and the zone ID to sort of create the connection.
Another question here, can CAD systems pass variables back and forth?
Yes, yeah, so I didn't really show that, but sort of another way you could go about this data exchange would be to use something like our watch window in HyperX, which contains all the same design results that were showed in the legend. And I could add, for example, is my screen share still coming through? There it is.
Yeah.
Perfect. Yeah, so I could add something like the the skin thickness to the watch window, and then it's in a tabular format. And assuming that the CAD model on the designer's end was parameterized, it would be easy enough to punch this out in like a CSV file, and push those dimensions in that way. Any other questions? Got a few more minutes.
I suppose while everyone's thinking about it, I'll leave everyone with one last thought here. This release that came out earlier this summer, 2025.1.4, all of the features that August showed are available in that release. And this is the first release to really include this comprehensive effort, and CAD is still very much a big part of our internal development effort. So you can understand that this is just the beginning, I would say, for CAD and HyperX.
Yeah, and with that, definitely open to any suggestions that anyone might have. whether you have them now or later on. I think everyone will have my contact info. Feel free to send them along.
Is there a recording? Yes, so we will be sending out a recording of this session to everyone that attended or registered this webinar for this webinar.
I see another composites question. What is exported to CAD for composites? Yeah, I'd be happy to talk that topic for a second. So there's a few different things that we currently support for that. There's kind of this generic export that you can do for composites, where HyperX can generate ply boundaries from its optimization results, obviously. So we can generate CAD curves that sort of fit the boundary of each ply, and we can export those in, again, any of the generic CAD formats, STEP or IGES. And then we have some software-specific formats as well. A new one being the FiberSim HDF5 format, so we can export our full ply definition in a HDF5 file, which includes the stacking sequence of the plies, ply orientations, and all that. And then we have kind of a similar export workflow with CATIA as well via a spreadsheet, XLS spreadsheet file.
Okay, well, I believe that takes us to the end of the session. Once again, thank you everyone for joining. Like I said, we will be sending out a recording of this webinar. And many thanks to you, August, for presenting.
No problem. Thanks all for attending. Have a good day.